Yes. Now it's good? Yes.
That's great. Now you can just repeat the statement. It would be great.
Yeah, okay. So, right. So back to the reduction theorem. So I'm not sure whether the conditions will be exactly the same as last time. So let's say G is a compact, or I mean, compact, probably one can relax, but it's easier if we assume the group is compact, connected Lie group. And then we have a Hamiltonian G space with a moment map, mu. So this is Hamiltonian G space. And finally, we have one more piece of data. So psi in G star, irregular value of mu. And for simplicity, we also assume that G psi, which acts on the fiber, so this action is free, right? So these were conditions of the theorem. And then the conclusion is as follows. So the reduced space, the reduced space M psi, which is the quotient of the fiber by the stabilizer, is a symplectic manifold. And so we have this diagram, the fiber of the moment map embeds into the ambient space and projects to the reduced space. And we have the following equation. So the symplectic structure on the reduced space lifts to the fiber, and there it coincides with the restriction of the two form of the ambient space. So so that's the construction. We started the proof last time, and we're going to continue the proof. But maybe now let me just recall that the part of the proof that we have done already is the existence and uniqueness of a two form on the reduced space which verifies the equation, right? So that's a kind of beautiful but easy part of the proof. So there is a unique two form which satisfies this equation, and that we proved last time. But now, so what remains to show is the fact that it's actually a symplectic form, right? Now, that's again splits into two parts. The first part is easy. The second part, let's say, is more cumbersome or less easy. And before doing anything, let me recall that for projection pi xi, the map pi xi star is injective. So if we know something in the images under pi xi star, we know the same thing in the forms on M xi. So with that, I'm just proving that the form omega xi is closed. And this is a sort of easy stuff. So I compute pi xi star of d omega xi, and I hope to show that this is zero. So I exchange the pullback and the Durham differential. I can always do that. And now I'm using the equation in red. And now I exchange again the pullback with the Durham differential. And this gives me 0 because omega was closed. And now by injectivity of pi xi, I see that omega xi is also a closed form. All right, so that's half of symplecticity. Now, what we also need to show is that omega xi is non-degenerate. And that's the only, whatever, complicated or interesting part. And this is usually the case when you, or this is often the case, when you work with reduction, then different types of reduction, then non-degeneracy is typically where you need to work. For all the rest, I mean, I don't know whether you recall the proof of this equation in red last time, or as you see, the fact that omega xi is closed, this is really easier. The fact that omega xi is non-degenerate is slightly more tricky. So let's see how it works. So I choose a point of the reduced space, and I choose another point on the fiber of xi, which lives in the preimage of M, and this is inside the fiber. Maybe let me try to make a drawing. So this is M xi, and here over M xi is sitting the fiber, and we have our point M, and that's the fiber of the projection map, and here is some point M tilde. So this is the projection map. So that's the picture. And now, well, a little bit of geometry. So the tangent space to the fiber at the point M tilde modular G psi M of M is Tm M psi. So any worries about this equality? So this G psi M is a tangent space to the fiber of the projection, right? Because we are dividing by the action of G psi when we go down along the projection. And so if you quotient the tangent space at M tilde by the tangent space to the fiber, you obtain the tangent space to the base. So everything is happy about it.
So do you denote it like this because it is canonically isomorphic to Lie algebra of stabilizer?
Yeah, right. Yes, that's because M psi by definition is a quotient by the free action of G psi. So each fiber of the projection is like a copy of G psi. And the tangent space to the group G psi it's Lie algebra because it's a group, right? The tangent space to it is identified with its Lie algebra. Is it convincing?
Yes, it is clear.
Okay, thank you. Okay, so right, so that was the first observation. Now the next observation, it's using that proposition that we proved last time. So so first of all, this T m tilde of mu minus 1 of psi, so the tangent space to the fiber. So that's exactly the orthogonal complement of the pullback pullback forms that you can get from the target of the moment map. So this map, the tangent of the differential of the moment map, it maps the cotangent fiber at G star, and this is just G star itself. It maps it to the cotangent fiber at M tilde. And whatever is in the image of it, these are forms which vanish on the tangent space to the fiber. That's because the fiber is exactly the preimage of psi. So that's where the forms that you can pull back from the target of the moment map, where they vanish. So as I'm saying, right, here we're using a little bit of geometric intuition. Is it clear what's going on here? So by definition, the fiber is consists of the points where the image of the moment map doesn't change. Okay. So now we have a proposition which tells us something about this this space, and I think it is telling us that T m tilde mu minus 1 of psi omega. So I want to know what is the omega orthogonal of this subspace. And well, I'm replacing it with the image of dm tilde mu transpose orthogonal. Sorry. I think the proposition is telling me, yeah, here I also start getting confused. What does the proposition that we had before was saying? Let me tell you the answer. So I want to come here. So the symplectic orthogonal of this tangent space should be equal to GMM. Now, is it true? Could you recall me what the proposition was saying? Right, the proposition. So the proposition was saying that image of dm tilde mu transpose orthogonal was equal to GM M omega orthogonal. Is it right? So there was a proposition last time.
Da.
Okay, that's perfect. I think that was the proposition was saying. So right. So now I can complete my proof. Right. So here I'm just using the first observation, and now I'm just adding omega orthogonal. And so this is then equal to GMM omega orthogonal, But if I do omega orthogonal twice, I simply get back what I wanted. Yeah, sorry. You know, with many steps, one is also getting confused. All right. So the omega orthogonal of this guy is GMM orthogonal. And here maybe a small remark. In case of G psi equal to G, then the fibers are actually quasi-tropic. Right? The fiber carries an action of G psi, but if by any chance the G psi is just equal to G, this means that this omega orthogonal of the tangent space to the fiber is contained in the fiber, right? And this means that the fiber would be quasi-tropic. So, for instance, this is always the case if G is abelian. Right? Then the coadjoint action is trivial, and for every point, the coadjoint stabilizer is just the whole group. Okay. Okay, good. So now the next observation is that this omega orthogonal to the fiber intersection with the fiber itself, with the tangent space to the fiber, is exactly equal to the span of fundamental vector fields for G psi. That's more or less by definition, right? If you had some other vector fields in this intersection, they would be preserving the fiber, and they would be in the Lie algebra of the stabilizer, right? So if you have something which is in G of M, but which is not on G psi of M, then it would be moving your point outside the fiber of psi, right? So, right. And so this left-hand side is by definition is the kernel of the restriction of omega to the fiber, right? So you restrict omega to the fiber, then this two form was non-degenerate, but now perhaps it is degenerate. But what does it mean to be degenerate? So there are some vectors which are contained in the tangent space, which are omega orthogonal to everything in the tangent space, and that's exactly this gadget, right? These are the vectors of the tangent space which have a zero omega pairing with everything in the tangent space to the fiber. All right, so now the last step. So I'm now saying I'm choosing some U in the tangent space, and I'm lifting it upstairs such that the projection of U tilde is equal to U. So then omega psi of UV is equal to, now I'm also lifting it upstairs. So this would be, by definition, this restriction of omega upstairs applied to two vectors. And here, of course, V tilde is also the lift of V. Right? And let's assume that this is zero for all V. right? So I want to check whether my form is non-degenerate. So I assume that there is something in the kernel. Okay. So then I know by the construction above that this means that U tilde is in the kernel, and the kernel is jigsaw of M. Maybe I should say M tilde.
Excuse
Yeah.
me, can I ask a question?
Sure.
How are we intersecting tangent spaces in different points? M tilde and M.
Oh, is it right? Yeah, you're right. Of course, I should have written M tilde. So it's all happening upstairs. Right. Okay, so this, it looks like this vector U tilde is in the span of the action of the stabilizer. But then what does it mean for U, right? Pi xi was a projection. So,
Can you scroll down a little bit, please, Anton? We don't see the bottom line. It's hidden. It's better, thank you.
Okay, sorry. It's interesting. So you don't always see my screen?
It's the first time I ever saw that I didn't see your screen, but it's just...
Okay, sorry. Thanks for saying it. Right. So if U tilde is a tangent vector to the fiber of pi xi, this means it projects to 0 downstairs on the reduced space. And this means it is 0 as a tangent vector on the reduced space. And this means finally that omega xi is non-degenerate. So you see, I wouldn't say it's very complicated, but it's sort of cumbersome, right? So that's the only part of the proof which is not straightforward, and that's how it usually works. When you do reduction, various versions of the reduction theorem, normally everything should go very smoothly because reduction is made to be nice and easy. However, the non-degeneracy is usually the most tricky point, and that's the place where you need to pay attention. So here it all converged. I'm not sure whether I presented it in the best way, especially in the beginning. I forgot part of the proof, and you helped me to recover it. But at least this is typically sort of a little bit of a non-trivial step. And of course, the most important point was that here we were able to compute this kernel, right? So the kernel of the restriction of the two form to the fiber, and it's directly related to the action of the stabilizer. So that's basically the key point. All right, so now we'll continue and do one example, then a little bit more of theory, and then again an example. And in the meantime, Ian, you wanted to paste the next problem set?
Yeah, good for reminding me. Yeah, do that right.
Chat. And I must say, yeah, we had a little bit of a discussion. I think this next problem set is too long. But then Ian was advocating that you want to have more problems in the problem set. I don't know. We'll see.
I said it's good to push them. That's a different matter. Whether they want to or not, it's good for them. I see that they respond.
I didn't want to
reasonably.
I was protecting you. I didn't want to tell people. That,
in this sense, no. But the other thing is that actually they're not. Some of them are doing the exercises at home, but the ones who come into the seminar are actually not doing them. They discuss it in the seminar, and I'm enjoying the discussions. But
okay. So a very easy example. So we consider M to be R to the power 2n plus 2 with the standard symplectic form. We can also identify it with Cn plus 1. So we have omega standard to be I/2, and here sum from 0 to n, and you probably already figured out why I want now the indices to go from 0 to n instead of from 1 to n plus 1. So, sorry, k. So dzk bar. I'm taking the group to be just a circle. G to be S1. It acts on our Cn plus 1 by rotating all coordinates in the same way. So it's a diagonal action. So the moment map, and I must say, after the last class, Ian told me that I'm always getting signs incorrect. I'm not sure always. I think it's random.
I don't think it's a big deal, Anton. I just
right.
made that.
Still, I tried to recompute all my signs. I'm not sure it's very efficient, right? Because if you have a person, he typically fails in computing signs, it's not clear whether recomputing gives a better result. But in any event, we'll see. I tried to recompute my signs, but I do encourage you to check whether there is anything correct about those signs. So I got mu of z is -1/2 sum of z squares. Now, well, we can do reduction. For that, we need to, so this mu -1 psi, this will be those n plus 1 tuples in Cn plus 1, such that -1/2 sum of k zk square is equal to psi. Obviously, this psi is better be negative or 0 in order to get a non-empty level set. And of course, it's convenient to use notation. Psi is -1/2 rho square. So it's less or equal to 0. So this equation now would read sum over k from 0 to n zk square equal to rho square. So actually the level set now has a clear meaning. It's a sphere of radius rho. So the level set, right, is a sphere of dimension 2n plus 1 and of radius rho. So we know how it looks like. And we have an S1 action on that sphere. So m psi is mu -1 of psi over S1. And you probably recognize it is isomorphic to CPN. So you divide this sphere by S1, you get CPN. Maybe maybe we can add just a small comment. So here in the fiber, right, we have points Z0, Zn, which satisfy the condition sum from 0 to n zk square equal to rho square. And the map to CPN, the identification with CPN, you're simply mapping it to the point of CPN, which is defined by the same coordinates, right? And this map descends to the quotient, right? Because the quotient by the diagonal action of S1. So this map descends to the quotient. To the quotient xi. So now of course, we know that that the formula. So the formula xi star omega equal to pi xi star omega xi. We know theoretically that this formula uniquely defines omega xi, right? So the formula on the ambient space is just this one. So the question would be whether we can get, you probably all have seen the Fubini study to form on a projective space, CPN. Now the question is, can we reproduce it? And so I've done an exercise. Let me just report. I must say it took me some minutes or tens of minutes to do the exercise. So let me just give you the answer, and then I encourage you to look at it. So let's look at the chart 1, Z1, so on, Zn. Inside CPN, right? So Z0, we just choose to be equal to 1. So then the calculation gives the following. Omega xi is equal to I rho square over 2. And here it gives the following well-known, but still kind of interesting expression from 1 to n, right? dzk wedge dzk bar, and here 1 plus sum over L from 1 to n, ZL squared minus sum over.
I would expect it's rho squared plus the sum, isn't it?
It's rho squared plus the sum. Wait.
Natural. It's not natural, at least.
Wait. Let's say ST ZS bar DZS wedge ZT DZT bar over 1 plus sum over L from 1 to n ZL squared. Sorry for bad writing. Now, good. So the discussion is open. So Ian has
retract that. I think it was a mistaken remark. It's a mistaken remark.
Sorry?
My remark was mistake, sorry.
Okay. So I think that's, frankly, I think that's the right formula. So the other experts in the audience, do you agree with the formula? I think it looks good to me.
No, it looks fine. It looks fine.
Yeah. Maybe one remark though. So first of all, of course, you probably all have seen this this expression, this Fubini study to form, or maybe you've seen the Fubini study metric, and that's the corresponding Keller form. Now, still, I think it might be an interesting experience if you've never done it. Start with this formula, right? This formula, after all, looks much more naive, right? It's just dzk bar. And now we just go through this very, very simple reduction procedure. And we do get some kind of, an interesting formula. I was fighting for a long time when computing it for this class, just for myself, with a factors of 2 or something. But I mean, yeah, at least it doesn't look completely obvious. Now, perhaps one interesting remark. Sorry, I meant to do something else. So let's look at this prefactor. So let me recall that it's equal to minus I times psi, where psi was a level of the moment map. Right here, I'm just using this formula. And what is interesting, omega psi, the denominator outside the sum. Yeah. So what is interesting, the whole thing is linear in the value of the moment map. So, and that's actually an interesting observation. This observation will play an important role in our course. It's some kind of general situation. So typically, when we do reductions at different levels, notice that here also we do reductions at different levels. The topology of the reduced space doesn't change, right? So CPN, so you get CPN basically independently of psi, unless psi crosses how people call it, the wall at psi equals 0. So you have basically the same reduced space, but the two form depends on psi, and it depends on psi linearly. So that's for the first time that we see it in the course, and later on in the course we're going to see it often. We're going to see it many times, and it will be important. Actually, I think there is at least one exercise in the next problem set which also focuses on that phenomenon. So here we get CPNs, and there we encourage you to work with Grassmannians. So a somewhat more general case. All right. So now I want to develop the theory a little bit more before going to yet another example. And here I want to tell you something about reductions of structures. So you see, we've done now a reduction for two forms. But when you do reduction, many other things also go through. And that's very, very interesting and very important. And probably this was the first motivation to do reduction. So we'll look today at the reduction of two different structures, which are actually related to each other. So let me repeat the setup. So we have our Hamiltonian G space. So we have our Hamiltonian G space. And now we choose a function, say a smooth function on M, and we assume that it is invariant under the G action. Right. The G invariant function. And we consider the Hamiltonian vector field of this function on M. So it's defined by this, uniquely defined by this condition. So this is a Hamiltonian vector field. And we're looking at the corresponding dynamical system. So phi th, M to M, is a Hamiltonian flow of the equation mt dot is equal to VH of mt. Right. So that's a kind of standard story. This is our manifold. That's our point M, and the vector field VH moves it in the manifold. Okay, so here is a simple proposition. which says the following. First of all, this flow phi t of h preserves fibers of the moment map for any xi. So we move along the fibers. Now the second observation. So there is a unique smooth function on m xi such that, and let me write it in two ways. So just to make it similar to what I was writing before, I write it this way. But actually, these functions, we usually don't write equations with pullbacks, right? It's probably better or like more consistent with standard notation to write it like this. Right, so these functions we kind of, that's the same, right? And finally, one more, and that's probably the main conclusion. So you can move the point m tilde by phi t of h upstairs and then project, or you can move the point on the quotient space by the Hamiltonian flow of h psi, and this is for any m tilde such that one of them is in the preimage of the other. So here maybe again what happens, right? So you have here m psi. Maybe let me draw it two-dimensional, or try to draw it two-dimensional. And here upstairs, there is mu minus 1 of xi. So there are points m and m tilde related by pi xi. And I can run a Hamiltonian trajectory. And I know that the endpoints will be also related by pi xi. So I don't quite know whether you have seen this idea, maybe in PDEs or ODEs, in some, maybe you had a mechanics course. I'm not quite sure. Is it completely new for you, or that's the first time you see such a thing?
So this is like a Noether's principle for mechanical systems.
Yeah,
we have a group of symmetries of Hamiltonian action.
Mm-hmm. Yeah, that's the Noether's theorem, exactly. Yes, you're right. So I guess, right, you've seen it in one form or the other. So let me still give a proof of the proposition. So that's an easy proof, but this gives you an example of a reduction of structures, right? So before I had a reduction of symplectic forms, but now I said, oh, let me add one more structure, right? I have a Hamiltonian G space and a G invariant Hamiltonian evolution on it, and it will also descend. So let me give you a proof. So first of all, it's essentially, you're right, it's a sort of version of the Nurse's theorem, especially the first point. So suppose I apply VH to the function given by the pairing of mu and x, right? So that's the same as contraction of VH with the differential of mu x. And by the moment map equation, it's the same as iota VH of iota xm of omega, right? So now I'm doing computations upstairs. Or I can exchange the contractions. This gives the minus sign. And now I'm using the definition of the Hamiltonian vector field. And this is equal to minus Lie derivative of H. And this is 0 because H is G invariant. All right. So, just to make an explicit link to the Nurse's theorem, right? The other way to say it is that mu x is a conserved quantity. And this is and that's the Nurse's theorem, right? So if you have a symmetry, you have a conserved quantity. If you have a conserved quantity, you have a symmetry. Right. Okay. So now the second point in the proposition was more or less trivial, right? We just define h psi of m equal to h of m tilde for any m tilde in the pre-image of M, and this is well defined, right? Again by G invariance. And so now the last thing that we need to check is that the vector field, or the Hamiltonian vector field upstairs, descends to the Hamiltonian vector field downstairs. So so what are they? We have iota VH omega is minus DH, and iota VH psi omega psi is minus DH psi. That's their definitions. So now I take the first equation and I apply iota psi star H omega DH, right? So now what we can do, we can observe that this is iota psi star, and here this is right. So here we know already that VH is tangent to the fiber, right? So we can exchange VH and the restriction to the fiber, right? So that's the same. So that's because VH tangent to mu minus 1 of psi. And on the right-hand side, I exchange the drum differential and the pullback. So now what? Now I probably do this. I'm using the reduction formula. And on the right-hand side, I'm also using the reduction formula, right? And I think now I do the most problematic step. Perhaps you can comment on whether I have a right to do it. Or maybe let me better do it this way. Right. So what do you think about this step, especially about this gadget? So I'm saying that I can exchange. So I was taking a pullback of omega psi, and I was contracting with a vector field. And I'm saying that instead, I want to contract downstairs with the push forward of that vector. So what is your expert opinion? Do I have a right to do it? No opinion? You see, there is a catch. So a priori, right, this push forward does not exist. Of course, each vector you can push forward, but if you have many preimages, maybe push forwards from different preimages do not agree, right? So this is a possibility. Let's forget about it for 1 second. In principle, I could have proved that the preimages actually all agree, but I don't want to do it. So I want to get it for free, right? I don't want to work too much. And let's do the following. Remember that pi psi is injective, right? So pi psi is injective. This means that I get the following equality, a tentative equality for a moment. Right? So that's because I can just take away pi psi star. So pi psi star was injective, so it doesn't matter. But now you see omega psi is a symplectic form. So it is non-degenerate. If it is non-degenerate, this means that those vectors, maybe those vectors coming from different points were different. Fine. But now they all satisfy this equation. But this equation defines them uniquely, right? Because omega psi is non-degenerate, and this means that they are all the same. All the vectors coming from different points, they could have been different, yes. But actually they are not, they are all the same. So they are the same. And this means that actually this pi psi star VH is well defined. It's kind of, in the beginning, we don't know whether it exists, maybe not. But now we know. Of course, in principle, this is, one could have checked that they all agree by hand. But I thought it would be fun to not do it and then still see that our equations magically do it for us. So that's the end of the proof, and we see that there is a reduction of structures, which is nice. And you're going to have some quite easy problem using this version of the Noether's theorem in the problem set. So maybe just to tell you, in general, people are using reduction. In most cases, people are using reduction in the following way. So the ambient space is supposed to be easy. The reduced space might be complicated. So for instance, the evolution, the Hamiltonian vector field and the Hamiltonian flow on the ambient space should be easy. Otherwise, the game does not make much sense. And then the reduced flow might be complicated. Of course, in our example, in the problem set, it is not that complicated. All right. So I would like to continue with one more proposition, or theorem, and then I'm not going to prove it, and this is part of the next problem set. So this is another example of reduction of structures. So proposition. Suppose we have G cross H Hamiltonian space, and here we had some kind of interesting scientific discussion with Ian about the notation. So we have a direct product of two groups. They both act in a Hamiltonian way. The actions commute. They both have moment maps. So we denote this moment map by product moment map. So this is a Hamiltonian G cross H space. And we assume that zeta in G star is a regular value of mu G. And of course, by now we know what we want. G psi acting on mu minus 1 of psi is a free action. Okay. So then the conclusion is m psi. Oh, sorry. Let me state it a bit differently. So the H action and mu H descend to the reduced space. And the reduced space becomes a Hamiltonian H space. I think in the previous problem set, you have already seen such an example when we were doing cutting, right? Cutting is an example of such a situation. So here is the general framework. You have two actions which commute, and you do reduction under one of them, then you get the action of the second gadget, of the second group on the reduced space. Again, it looks a little bit silly, but that's one of the things which people are using in like hundreds or thousands of papers to develop relatively non-trivial stuff. So this is a simple but very, very powerful tool. And I think I'm suggesting this exercise as one of the exercises for the next problem set. So I want to end today's class with one application of this theorem. And so let me first make a setup and then introduce the construction. So recall that we have an example where we have two commuting G actions, and that's a Hamiltonian action on T star G. Well, again, Ian said that I computed all these signs of moment maps incorrectly. Yeah, maybe that's right. Or I don't know.
I mean, I precisely didn't interrupt you last time to talk about it. I didn't think it was worth mentioning. But I mean, if you really insist, I can show them to you. But I think it's a triviality.
Yeah, let's see. I now recomputed the signs. Maybe they're wrong again, or maybe they're right. I don't quite know. So let me say. So that was one of the G actions, and my recomputed moment map is minus P, and the other G action is like this. And my recomputed moment map is G minus 1 PG. So how do those signs, Ian? So how do those signs look like? Are they now?
Excuse me, I was.
Are they now?
Sorry, I wasn't looking to. Sorry, I'm usually looking at what you do, but just for a moment, I did.
Okay, yeah, but okay. Let's say you will see. It doesn't matter that much, but
well, I would probably put them the other way, by the way. But anyway, I really don't know. I honestly don't know. I cannot say. I would guess that they were the other way around, and I think they were the other way around last week.
Okay, believe it is an open research problem, right?
It's not important.
Okay, so we do the reduction under the first action. The first action. So we fix the moment map. So mu, let me call it G mu1 and this one mu2. So let's fix mu1 of GP is equal to minus psi. So we do the reduction at the level minus psi. Of course, this implies P is equal to psi. Right. So what's the level set? Now this is very easy, right? So these are points GP with P equal to minus psi. So this is isomorphic to a copy of G. Now, what's the G action? Or better say G psi action. So G psi should act on mu minus 1 psi. And well, this action is like this. P maps to H, P, H minus 1. But now H is in the stabilizer, right? So this is, of course, equal to P and is equal to psi. And then G maps to HG. And this is an action by left translations. This is, of course, a free action, right? This is always a free action. Well, now the reduced space, M psi, is isomorphic to, let me denote it in this way. So this is just a quotient space, right, of our copy of G by the action of G psi. And by the proposition that we had before, so we have a moment map, which maps it to G star, and this moment map is mapping this this element of the quotient space G psi G to G minus 1 PG, which is equal to G minus 1 psi G, or in more abstract notation, which is equal to adjoint star G minus 1 of psi. Right, so this map, mu2, is establishing an isomorphism between the reduced space and the coadjoint orbit, right? So, so M psi is isomorphic to adjoint star G minus 1 of psi for G in G. And this is a coadjoint orbit of psi. So, right, here is a conclusion from this example. Coadjoint orbits of G Hamiltonian G spaces under the coadjoint action with moment map the embedding back to the dual space. So in fact, I don't quite know whether you've seen that statement before. In any event, there is this Kirillov's book on orbit method. And there, at some point for some other lecture series, I looked it up. So he gives 3.5 proofs of this statement of construction of canonical symplectic structures on coadjoint orbits. And this is one of the proofs that we did now using reduction. There is also a direct proof, and I don't quite recall now what are the other 1.5 proofs. But I certainly encourage you to have a look. I don't quite remember how he's doing it, the other constructions. Also, the name of those symplectic forms is Kirillov constant Suryo, or often people say KKS, symplectic forms, or also canonical symplectic forms on coadjoint orbits. One should also say that people over time, since discovery of those symplectic forms, which is probably sometime in the 70s of the last century, there is an infinite number of research which happened on investigating symplectic structures on coadjoint orbits. Just from my own experience, about 30 years ago, when I was starting my research career, I was working on certain symplectic forms on coadjoint orbits for infinite dimensional groups. And now, you know, sometimes the development of science is periodic, and now recently it became of interest again. So now I'm again working on certain symplectic structures on coadjoint orbits. So just to tell you that this is, on the one hand, looks all elementary. On the other hand, in somewhat non-trivial examples, these are this is still kind of interesting research which is going on. So I want to finish today's class with the following proposition. So suppose you have a Hamiltonian G space, which is a homogeneous space. So it is G mod some subgroup. So here there is some omega, there is a moment map. So a homogeneous Hamiltonian G space. So then M is a cover of some coadjoint orbit. Okay. So basically, if you, of course, sometimes write homogeneous spaces, that's one of the things that we often consider in geometry, because we have a lot more control over homogeneous spaces than over other things. And so it turns out that if you look at homogeneous spaces, that basically you have coadjoint orbits and their covers, finite or infinite covers, depending on the situation. Of course, in many situations, there are no non-trivial covers at all. So if your coadjoint orbit turns out to be simply connected, then it doesn't have any covers. So then that's it. If you have a homogeneous space, it is just a coadjoint orbit. So proof. So first of all, write the moment map is equivariant. Right? So the action, we know that the action on M is transitive. And this means that the image is a coadjoint orbit. So you take any point in the image, right? You act by the group, whatever you get by equivariance, it's an orbit of that point. So the image is a coadjoint orbit. Now, in principle, what may happen, right? We know that the stabilizer of a point in M is contained in the stabilizer of its image, right? That's just by equivariance. But of course, the stabilizer of a point in principle might be smaller. So, so we have a similar embedding for Lie algebras. And now let's assume that we have some element X, which is not in GM, but which is in the jigsaw. So then the moment map condition tells us that the contraction with the two form is the differential of mu psi. Let me write it in a somewhat strange way. Let me say that this is a mu star of the differential of minus the moment map of the orbit paired with X. So here I'm doing the following. I have M and I have mu, and I know that mu maps it to some coadjoint orbit, and then I embed this coadjoint orbit into G star, right? Of course, and I call it mu O. I have a right to do it. This mu O is basically the identity, the embedding of the orbit into G star. So then notice that this would be mu star. And here I will have iota of xm with the symplectic form of the coadjoint orbit. I denote it omega kks, right? But now, if x in g psi, this means that x at the point psi where I'm computing, right, is just equal to 0. The kind of an element of the stabilizer by definition doesn't move your point. So this means that this is 0. And this means that this is 0. But this means that xm at the point m is 0. And this means that x is in gm. So the conclusion is gm is actually equal to g psi, and then gm, sorry, and this means that and this means that g psi mod gm is a discrete group. Is a discrete group. So gm is a connected component of g psi. So g psi mod gm is a discrete group, whatever it is. And this implies the statement that we wanted. So let's call this guy gamma. So m to m mod gamma is a covering space of the orbit. In fact, maybe the last remark. If G is compact, then gamma is always trivial. However, again, in your problem set, there is an example where in some cases you can have a non-trivial gamma. So this is the SL2R example. You can check. We don't ask it in the problem set, but some of the coadjoint orbits are not simply connected. And then, of course, they do have symplectic covers, which may carry actions of some interesting groups. All right, people, that's it for today. I don't know whether you have questions about the class or whether some of you want to stay and talk more about the application story.
I have a question.
Mm-hmm. Sure, go ahead.
In the last theorem, the form omega on the homogeneous space, is this some kind of a specific form, or?
Oh, we just ask it to be Hamiltonian G space, right? Of course, when we know the statement, now we know what it is, right? So M is a covering space of the orbit, and omega is a pullback of the KKS form. So that's that. But that once we know what the structure is, then so it is actually a specific form. But in the beginning, we're just saying, oh, let's take a homogeneous Hamiltonian G space. So the form has to be, of course, G invariant, and we should have a moment map.
Okay. And I have another question that's about science.
Yeah. Okay.
Yeah.
Yes.
Actually, in the last couple of lectures, we had two different definitions of fundamental vector fields. So that we will use it.
Yes.
I will use it.
I think that was one of them is probably wrong, right? I agree. That's what Ian was
Probably.
saying. Yeah, you're right, because I think the good definition of fundamental vector fields is when a fundamental vector field defines for you a homomorphism of Lie algebras, right? So you want a homomorphism from your Lie algebra to the Lie algebra of vector fields. And I think probably one of my definitions, the wrong one, was an anti-homomorphism, right? So if you change sign, instead of a homomorphism, you get an anti-homomorphism. Fortunately, it doesn't change much of the conclusions, but certainly, yeah, so sorry for kind of being not sufficiently careful with those signs. But I agree with you and with Ian. I think it's mainly last time that I was probably using a wrong definition of fundamental vector fields.
Well, I don't think
Your sound is not very stable. But yeah, I agree.
the change of the sign changes homomorph. So, okay.
Yeah, I'm not sure we hear everything you're saying.
So we will not care.
Okay, when kind of on some other occasion when your sound is good, we can rediscuss it. But I agree, the signs were not very consistent, and that's bad. All right, more questions about the course? All right, so
Thank you.
Yeah. If not, people, I see you next week. And those who want to talk about the application procedure, please stay.
So I will bid you farewell. I guess I don't need to.
Okay.
Just switch the recording off, probably.
Yeah, right.